Okay, so here is a step-by-step procedure of how we are going to be finding zeros, finding roots, finding x-intercepts of polynomial functions. So we're going to use I'm not going to read all these words to you, but we're going to use the rational root theorem to find a list of all the possible rational roots. Remember that we might find a big giant list and none of them work. That's always possible. But hopefully we'll find at least one rational root that does work. Then we're going to use synthetic or long division to factor that corresponding factor out, reducing the degree of the polynomial. And we're going to keep repeating that process until we get down to a quadratic. Once we get to quadratic, we can just use like college algebra, intermediate algebra level factoring, or quadratic formula to find the last two roots. So, like, here's a quick example. We've got this third degree polynomial. It's going to have three roots, not necessarily distinct. We might have repeats. We're guaranteed of that. So we use the rational root theorem. We want factors of -1 over all the possible factors of 4. So the possible rational roots are plus or minus 1, plus or minus a half, and plus or minus a quarter. Like, I don't want to plug a quarter into here and see if it works. That sounds nasty. So I would start with 1. Start with the easy ones. So if we do, like, one way to check and see if 1 is a root is use synthetic division and see what remainder we get. We get a remainder of 0. Remainder of 0 means we got ourselves a root. It also means if we factor out x minus 1, these will be the coefficients of the lower degree polynomial that's our quotient. So this guy here could be factored x minus 1 times this quadratic. So you look, the 4, and the 1. And it's always x minus whatever number you have out here for this factor. That guy there does factor. There's a little missing piece of the slide here. That guy is 2x plus 1 times 2x plus 1. So we've got a third degree polynomial. We've got three factors. We'll list them all here. X minus 1. Third degree polynomial guaranteed to have three factors, not necessarily distinct. We've got a repeat here. We get three roots. We get x equals 1. Set this equal to 0, and we get negative a half. So that guy pops up twice. We do get three roots, just this guy popped up twice. And now, of course, we know how to graph polynomials. That's our ultimate goal here, is graphing. So our leading coefficient is positive. Our degree is odd. So we know our arms are going to go down, up, opposite ways because the degree is odd. The one on the right goes up because the leading coefficient is positive. So our arms are going to go like this. We know we've got a root at -1/2, so an x-intercept at -1/2, 0, with a multiplicity of 2, meaning the graph is going to bounce off there. And then we have to pass through at x equals 1 right there. What about our y-intercept? How do we find that? How do we always find the y-intercept? We plug in x equals 0. There's our y-intercept right there, 0, -1. So we've graphed that. Okay, let's look at another example. So we got this fourth degree polynomial. We're going to have four roots, not necessarily distinct, not necessarily real, definitely not necessarily rational. But we're going to start with the rational root theorem. And list out the possible rational roots. So we've got here, I'm going to make sure I'm consistent. P and Q. We call this guy P. We call this guy here in front 1, Q. So factors of P, we've got plus or minus 1, 2, 5, and 10. And over factors of Q plus or minus 1. So all these different fractions, so the possible rational roots, every possible fraction that we can make with factors of this guy on top and this guy on the bottom. Plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10, because they're all over 1. Okay, so now we got to start checking them. I'm not going to start with 10. I'm going to start with the easiest one, 1. So I want to know when x equals 1 is question mark y equal to 0. I could use like synthetic division or long division and check the remainder, or I could just kind of plug in and see. What are we going to get here? We're going to get 1 to the 4th is 1. 1 cubed, like all of these x's are just 1. So we get 1 minus 3 plus 5 minus 1 minus 10. So that's negative 2, positive 3, 2 minus 10. It ain't 0. That didn't work. Okay, what about negative 1? Negative 1 to the 4th is positive 1. Negative 1 cubed would be a negative, which will cancel out that negative, so we get plus 3. Negative 1 squared is positive, so we're not going to change this sign. Only the odd powers are going to change signs. Negative, negative 1 is plus 1. And then that minus 10. That's 4, 9, 10. Minus 10, we do get 0. We've got ourselves one of the roots, negative 1. So let's factor it out and check. So I'm going to do synthetic division to do this. So my coefficients here are 1, negative 3, 5, negative 1, and negative 10. Bring the first guy down, and then it's multiply and add all the way through. Negative 1 times 1 is negative 1. Add straight down, negative 4. Multiply, we get 4. Add straight down, we get 9. Multiply, negative 9. Add straight down, negative 10. Multiply, 10. Add straight down, we get a remainder of 0. Yay. That's what we were supposed to get. If we don't get a remainder of 0, we've done goofed. But now I also have factored out x plus 1. So that original function, x to the 4th minus 3x cubed plus 5x squared minus x minus 10 could be written as x plus 1. Remember, the factor is always x minus the root times. Now, remember, these guys are going to have 1 degree less than what we started with. So this was 4th degree. These are going to start with cube. So he is x cubed minus 4x squared plus 9x minus 10. Okay, now I'm just going to rinse and repeat. Now I need to find factors of this guy. So I could start over, but anything that's in the list for him had to be in the list for the original. So here were my possible rational roots here. Anything that makes that quotient 0 had to make the original 0. I don't have to repeat the process. If anything, I'm going to lose stuff out of this list. I'll never gain new rational roots at this point. You might lose some stuff, but you'll never gain new stuff. So we just want to, using just this guy, I could plug into the original, but I don't have to. I can just plug in here and check and see what makes this 0. We could check 1 again. It's possible 1, or we know 1's not going to work. We could check -1 again and see if it's going to work. But you can quickly just glance through there and see -1's not going to work. So let's check 2. Again, I could do this with synthetic division. I already know it's going to work, so let's do that. Let's use synthetic division to check it. Or we could just plug in 2 and see if we get 0. Okay, so I'm going to write down all my coefficients here. Bring the first guy down, and then multiply and add. 2 times 1 is 2. Add straight down, we get -2. 2 times -2 is -4. Add straight down, we get 5. 2 times 5 is 10. Add straight down, we get a remainder of 0. Yay, we found ourselves another root. So we're going to have this guy here. Could be rewritten as x minus 2. Remember, it's always x minus the root. And now this is going to drop down 1 degree. I started with the cubic here. This is going to be quadratic. X squared minus 2x plus 5. Okay, now I could keep trying a bunch of rational roots. Or I'm down to a quadratic. Once you get down to a quadratic, either just factor using regular old factoring you've been doing since 8th grade, or just use quadratic formula. So now x squared minus 2x plus 5. We'll get x equals opposite of b plus or minus the square root of b squared, so -2 squared, minus 4 times 1 times c all over twice a. Remember, when you square a negative, it becomes positive. So when you're typing that in your calculator, you got to be careful. In fact, I recommend not even putting that negative in because you're going to square it away anyways. -2 squared is positive 4 over 2. 4 minus 20, of course, is -16. We're going to get complex solutions here, complex roots. Square root of -16 is 4i. And remember, when you're splitting these up, don't just cancel here. You have to write each one over 2 and then cancel in each fraction. So that's 1 plus or minus 2i. Okay, so now to summarize. This guy here that we had, to the 4th minus 3. I should have just copied and pasted. Sorry about this. -3 plus 5 minus 1 minus 10. His roots. He's a 4th degree polynomial, guaranteed to have 4 roots, guaranteed to have 4 factors. His roots were -1, 2, 1 plus 2i, 1 minus 2i. Make that look more like an I. His factors. It's always x minus the root. So x plus 1, x minus 2, x minus, and I want to put this in parentheses, 1 plus 2i. and then x minus 1 minus 2i. Fourth degree polynomial has 4 roots, going to have 4 factors, not necessarily 4 x-intercepts. These guys will not give me x-intercepts because they're complex. They don't show up in the real plane. These will. So my x-intercepts will be -1, 0, and 2, 0. My y-intercept, remember to find the y-intercept, you always just plug in x equals 0. Your y-intercept is always, if you're in standard form here, expanded form, your y-intercept, the value of it, the y value, is right there. 0, -10. We know our end behavior. Fourth degree polynomial, so the arms have to go the same direction, either both up or both down. My leading coefficient is positive, which means the right arm goes up. Leading coefficient's positive, the right arm goes up. Even degree, the arms go the same way, meaning now the left arm must also go up. So I can quickly sketch this guy's graph. I know both arms go up. I know I've got an x-intercept at -1, 0, another one at 2, 0. My y-intercept is down here at 0, -10. So my graph is going to do something like this. So there's a rough sketch of the graph. Is it possible there are more wiggles in here somewhere? Sure. We need calculus to find those extra wiggles. At this point, this is the best we can do, and that's a good place to stop.